Welcome to Polymatica. In this series, we'll explore the world of polynomials, one of the most fundamental, yet powerful tools in mathematics, from high school basics all the way up to emo-level problems. Polynomials look simple, just x's and powers. But they shape the laws of physics. They challenge the sharpest minds at the emo. And they even power the algorithms behind artificial intelligence. A polynomial in one variable looks like this: an times x to the power n, plus an minus 1 times x to the power n minus 1, and so on, down to a 1 times x, plus a 0. Here, the degree of the polynomial is the highest power of x. The leading coefficient is the number in front of that highest power. And the constant term is simply the value when x equals 0. For example, if p of x equals 2x cubed minus 5x plus 7, then the degree is 3, the leading coefficient is 2, and the constant term is 7. One of the most important facts about polynomials is the factor theorem. If p of r equals 0, then x minus r is a factor of p of x. For example, take p of x equals x squared minus 5x plus 6. Since p of 2 equals 0, we know that x minus 2 is a factor. Indeed, p of x can be written as open bracket x minus 2 close bracket, times open bracket x minus 3 close bracket. In general, any polynomial f of x can be divided by x minus a, giving a quotient g of x, and a remainder f of a. Here's a simple but powerful fact. A polynomial of degree q can have at most q roots. For example, a quadratic equation can have at most 2 roots. A cubic equation can have at most 3 roots. And if a polynomial somehow has more roots than its degree, that means the polynomial must be the zero polynomial. So what if we combine the basic properties and small bonus? Then we get a powerful conclusion. If a polynomial p of degree n has roots a 1, a 2, all the way up to an, and leading coefficient k, then p of x equals k times open bracket x minus a 1 close bracket, times open bracket x minus a 2 close bracket, and so on, up to open bracket x minus a n close bracket. This comes directly from the factor theorem. Each root gives us a factor, and multiplying them all together reconstructs the polynomial. Now let's prove why this formula is correct. Suppose p of x has roots a 1, a 2, all the way to an. By the factor theorem, each term x minus ai must be a factor of p, so we can write p of x equals q of x, times open bracket x minus a 1 close bracket, times open bracket x minus a 2 close bracket, and so on, up to x minus an. But here's the key point. On the left-hand side, the degree of p is n. On the right-hand side, the degree is degree of q, plus n. That means q must have degree 0, in other words, q is just a constant. Finally, what constant is it? The leading coefficient of p is k, and on the right-hand side the leading coefficient is simply q, so we conclude q equals k. And that completes the proof. Here is the example. One last note: if two polynomials p of x and q of x are equal, then everything about them must match. Their degree, their coefficients, and of course, their values. We'll leave the full proof as an exercise for you. And next time, we'll show you why this simple fact is so powerful. Here is our small example. In this exercise we can see that by using the substitution method and apply the tools skillfully, we have solved the problem. Last but not least, you can attempt these 3 problems to check your understanding. It may be hard if this is the first time you study Math Olympiad. But don't worry, because we are here to help you. Practicing problem is the best way to learn. We highly recommend you to take note what you have learned and spend time for practicing. Take note that asking AI for hints after some attempting may help you. That's it for today's lesson on the basics of polynomials. If you enjoyed this, don't forget to subscribe to Polymatica, so you won't miss the next episode, where we dive into Viète's formulas and harder polynomial identities. See you there. Polymatica, unveiling the beauty of math.